Well, good afternoon, everyone. It's a real pleasure to welcome back to WIN Dr. Ming Liu, who is Director of the Department of Nano-Fabrication and Integrated New Device Technology in the Institute of Microelectronics of the Chinese Academy of Sciences in Beijing, China. Dr. Liu, who was a visitor to WIN in 2011, and that, if you remember, is well before the Quantum Nano Center was finished, and she gave a seminar at that time. So we're happy now to have the opportunity to show Dr. Liu the new home of nanotechnology, research, education, and innovation at Waterloo in the new QNC building. Dr. Liu received her BS and MS degrees in semiconductor physics and devices from Hefei University of Technology in 1985 and 1988, respectively, and her PhD in material science from Beihang University in 1998. Her current research interests are in micro-nanofabrication, memory devices and integration, nanoelectronics, and molecular electronics. Dr. Liu holds more than 30 Chinese patents, with more filed and pending, and has published 3 books in collaboration with others. She's been a prolific researcher with more than 180 papers in refereed journals and more than 50 contributions, including 18 keynote or invited papers at international and national conferences. She was awarded the Elite Young Scientist Award from NSFC, the National Science Foundation of China, I believe, the highest honor which can be bestowed to a young scientist in China, and that was in 2008. She also received the National S&T Progress Award, second level, in 2009, and the National Invention Award, second level, in 2007 and 2005, as well as other awards from the Beijing government and the Ministry of Education. Dr. Liu is an expert on non-volatile memory and will speak to us about developments in STT, MRAM, and RRAM. So please welcome Dr. Ming Liu for a seminar, The Development Status and Challenge for Non-Volatile Memory.
So thanks for Professor Carty's introduction. I'm so happy to come here again. So unfortunately, it's not a right time because I know it's examination weeks. So I think everybody was so busy. So I'm so appreciate you in your very busy schedule still come here to my presentation. So before my presentation, I will give a little time to introduce myself, the institute. So here shows China maps. We can see the Chinese Academy of Science is the largest independent research organization in mainland China. So they have, actually now there are more than 100 institutes. They are distributed around China. Today, even the tobacco also have the separate institute that belong to the Chinese Academy of Science. But most institute is still focused on the Beijing and Shanghai. So this is roughly about the Chinese Academy of Science. But each institute, they are dedicated in a very dedicated special research field. So let's mean the Chinese Academy of Science covered almost every research field in the nature science, not for the art. So then our institute named the Microelectronics Institute. They are located in Beijing, in the north of the Beijing. So I personally think it's a very good location. It's very close to the bird nest. It's very famous for 2008 main stadium, for the Olympic stadiums. So because this area is not so much populations compared to other areas, there are a lot of, you can see a lot of garden, a lot of green areas. So also because today it's also very convenient. They have subway, public transportation. Transport is very easy. Go to other side of the Beijing. So I pretty like this area. Also, one important is because I also live here, very convenient from my home to my office. That's very lucky because if you live in Beijing, most people maybe spend 2 hours to go to office. So for our institute, we are the only institute in the Chinese Academy of Science dedicated on the microelectronics. So we are compared to a larger institute. We have these are all the numbers. Today maybe we have more than 1,000 staffs. Also some graduate students, also the post fellowships. So this institute have the history is long on, and I cannot say what's the long and short, because before we are the same institute with the Semiconductor Institute. So we trace back to the 1958. It's the same with the Semiconductor Institute. So that time is very government, because that time you know China is closed door to the outside world. So they have to do anything by themselves. In this situation, they decide to make their own transistor and circuits to build their own computers. That's why this institute to build up that time. But today, after so many years developing, today we have quite good facilities in our institute. For example, we have 3 separate facilities. One is the standard CMOS facilities. We can down to the 22 nanometers. So but this is still 8 inches. So this is very based on research, not in the mass productions. Also, we have the compound semiconductor lines. This is very flexible, from 2 inches to 4 inches. Also, we have more flexible lines is nano process facilities. In this facility, we can do some of the CMOS, advanced CMOS technology. Also, we can do some beyond CMOS technology. It's very flexible, not like the CMOS lines. A lot of material cannot enter these lines. So the basic facilities for the research activities in our institute mostly focus on the IC design and applications. So we can see with the ASCA designs for the RFID analog, also for the electrical systems like the navigation and the communications. Also some SOC design. Also the EDS Center belongs to the Chinese Academy of Science is located in our institutes. Most of this is based on silicon technology. So besides the silicon technology, we also have some based on the compound semiconductor. We are mostly focused on the electric device for the high frequency, for the high power device. I think also for the compound semiconductor material, there are a lot of guys involved in the light for the LED and for the another photonics research. But for us, we are focused on this area because we are little different with the Semiconductor Institute. That's why our research area also should have some distinguish. So also we have some fundamental researches both on advanced CMOS technology and beyond CMOS technology. So then I like to give some introduce of my departments. So I took a responsibility for this department 12 years ago. That time we only focused on the nano-fabrication and the mask making. So, but when I took a charge of this department, I think I have a lot of difficulty because only do nano-fabrication is very tough to get funding. Also, it's very tough to show what's your achievement. That's why I step by step to extend my research field from nano-fabrication to another different research fields. For the nano-fabrication, with a long history for this department, maybe almost 13 years. Basically, we do some optical masks. So also do some of the advanced lithography, like the nano lithography, e-beam, even we do X-ray lithography research for the nano printing like this. Also, actually, we do some of the optical lithography technology, like the OPC, optical proximity effect, like the PSM. This research also to how to improve the resolution for the standard equipments. we have supported more than 400 customers around the mainland China, also some abroad customers. So also do some of the national standards on the nano-fabrications. So for example, for the extreme EUV nano-opticals, so this is very challenging for the nano-fabrication because usually this is a device like the structure like this. The nano structures was short fabricated in the very thin films, not in the very standard the substrates. So also we should strictly control the line space. Even you should highly control the profile very well. So let's have very special application, especially for actual very short wavelengths application. You need a structure like this. So also we do some organic molecule devices. So based on some you see a lot of for the chemistry they invent a lot of they mix a lot of the materials. But how this material can really become a device and really get applications, we try to collaborate with them. At the beginning, we just how to developing some of the process technology can use for the molecular, because the molecular is totally different with silicon. So also based on this, we try to solve the big issues for the molecular device. Because for the molecular device, usually they are very high voltages. That's not good for the future radio applications. If you are familiar with this area, you see usually 15 watt for the operating voltage. That's very high compared to silicons. So also we try to understand some of the basic transport models for this kind of materials. In this area, actually there are two different background guys involved in this area. Mostly is the chemistry, their background is chemistry. So they use some of the quantum chemistry to describe this material. But for us, we still hope to based on some of the amorphous materials, their band structures, like the trapping models, to explain the transport properties. Because this is more easily to integrate with future device model and the compact models. Also, we do some of the real, some of the low-cost RFID on flexible substrates. For the memory, today I will introduce the RRAM, but except RRAM, we also collaborate with local industry to do some of the trapping memory for this area. We try to use the new material, also the modified the band structures to improve the performance for this kind of very traditional device. Also, we collaborate with the industry when they develop next generation technologies. How to improve their reliability is very big issues. So we use our knowledge to improve their new devices' reliabilities. Also, for another, with some circuit design, we really enter the market. So, for example, we are also developing the full process module for the embedded memory applications, collaborate with local companies. So, also for mask and mask services, we can provide the mask very flexible from 2 inches to 7 inches. Also, we are the largest providers for the research masks in mainland China. So you can see this customer distributions, even some abroad customer. That's because before they study in mainland China, they make masks in our institute. When they go abroad, they compile, then still ask us to give this kind of service. So let's roughly introduce our institute. Now I give my today's presentation. So here is the outline. Firstly, I will give what is the non-volatile memory. Then I will introduce it's a new kind of non-volatile memory named resistive switch memory. So because of limited time, I only introduce what we do in the how to understand the switch mechanism of this kind of memory. Finally, it's a very simple summary. So before, I like to very simply introduce review the history of this area. So compared to the traditional industry, microelectronics is a very young field. So, but in this developing histories, some of the very famous scientists, their contribution is dramatically. We are very familiar with these three guys from Bell Lab. They invented the transistors. This is basically lifetime from physics to device. That's the very important steps. So then almost 10 years later, two talent guys is Gilby from IT, the Noise from the Fairchild. They separately invented integrated circuits. But if you detail look at what's this, we can say GLB's the integrated circuit is just a prototype device. They cannot make the mass productions. But for Noise, so their designs is really can use for the mass production. That's because they use two technologies. One is they use pattern to realize the integration. Another is the planar. This structure as a structure. This structure is really important for this whole the microelectronic industries. But unfortunately, we all know only Gilby won the Nobel Prize in 2000. Noise, not because Noise died in 1990s. So also a very important guy is the Dr. Sa from the Illinois. He invented the CMOS these structures. That means in the not the off states, their pole consuming is equals 0. Also, this structure is easily to the screen down. That's the basis for the integration. Then there was more. I think everybody familiar with the Morse laws, but this is not really the physical laws. It's just predicting the industry, predicting the trend of these industries. The Noise and the Moore is a confounder of the Intel. So except this, all these guys, they are not a lot of big guys also contribute a lot for the. They invented for example, the DRAM is downloaded from IBM. Also, the non-volatile memory this is Professor Si, also from Bell Labs. Also, like CCD, CCD already won the Nobel Prize. Also, the CPU from Intel. So you can see from this history, you also can summarize some of the big guys' name recorded here. So after the almost 60 years developing, today the semiconductor is become an independent industries. In the 2000 last year, the total semiconductor market is around 300 billion. That's maybe this number is not so meaningful for me, but if you compare this, is occupied 0.5% total GDP. It's exceeded oil and steel. It's almost equal to the automobile industry. That means a very large industry area. So for the semiconductor, you not only can see the market value, you also can see the influence to the different areas. Not only for the industry, also even for everyone's daily lives. It's totally changed because the semiconductors are developing. So among a lot of different kind of circuits, the memory occupied one of the four total markets. That means memory is very important. So for semiconductor memory, we can roughly divide it into the volatile memory and the non-volatile memory. So what's the meaning for this difference? So for non-volatile, that means when you give the electric stress, you can keep store the data. When this stress is removed, the stored data also disappeared. That means volatile. So the opposite is non-volatile. Even after the data was stored, even they remove the electrical stress, this data is still kept. That's the difference. So for today, the most important memory is 3 kinds. SRAM, DRAM, and the flash memories. So the flash memory now is growing more and more importance. So let me say the difference. For SRAM, it is 6 transistors structures. That means you store 1 bit need 6 transistors. That means it is cannot realize the high density integrations. But this structure is very similar with the CMOS logical device. That means they are computer with logic. That's why you see all the computers, they use the cache to set up the computer. The cache is consistent with SRAM because the operator time is similar with the logical device. For the DRAM, it's 1 transistor, 1 capacitor structures. So for this structure, you easily can realize the high densities used for the working memory. So most of the computers' working memory is belong to the DRAMs. For the flash memory, it's 1 transistor with a floating gate. So for this structure, you can see it's very easy to see to realize very high densities. That's a different of a different kind of memory. Only flash memory is a non-volatile memory. That means when the data stored in this device, even the supplied port was removed, this data is still stored. But for SRAM, DRAM, totally is the non-volatile memories. So today I only focus on the flash memories. So this is a basic structure for the flash memory. If we know for the logical device, usually it consists with a source string and a gate. So, but a little different from the logical device is here have a floating gate. Usually, this floating gate is a conductor layer. It's a polysilicon. So, how to realize the programmed eraser? So, usually, when I give the stress, this channel, the electron will inject into the floating gate, then realize the program. So if you like to erase it, you use the opposite what you stress. That's the stored electrons inject the channel again, realize the eraser. You can see in this structure, when you program it, even you remove the actual supply, this data is still stored here. So that's why this structure can realize the non-volatile performance. This structure invented in 1967. So for the device size, it's very good performance, general performance. But for radio application, even after 20 years later, they can get radio application. Why? Because they still need to find the integration architectures. That's also important. So after almost 20 years later, both Intel and the Toshiba invented 2 different architecture, can integrate this very nice device. So finally, the flash memory get very dramatic developing. So we can see in the 1995, the first NAND flash memory was issued from Samsung. It's a 17.2 megabit. That's a U disk that time. It's very popular at that time. I think I remember that time I still purchased my PhD. The U disk is very expensive. So after during the 15 years developing, we can see today the floating gate cell, the scaling down more than 2,300 times, but the density increased 1,000 times. That means per year the increase each square millimeter the density increase 170 bit. This is very dramatic developing. Also the cost decreased largely. Today even the laptop they use their hard disk is also use the flash memory. That's why today's top layer can so light. But actually, when the full screen down, these basic structures also feel very big challenges. For example, this is a basic structure device. When they use the integration, the drain was connected with the bit lines, the gate was connected with word lines, and the source used a common source. So when the full screen down, that means the device and devices, they are connected very closely. Also because the storage layer is a floating gate, it's a conductive layer. That means the very tight neighbor cells will cause crosstalk problems. Also, for screen down this device, the channel becomes small and small. The electron inject into the floating gates become also less and less. So we can see the electron can enter this floating gate. Also, when the full screen down, the bit lines leakage increased dramatically. That means this basic structure faces very large challenges for the full screen down. So at these situations, two ways we should the innovation. One, to look for the basic structures innovation. At this size, a lot of different kind of new device structure was proposed. For example, the charger trapping, resistance switch memory, phase change memory, STM-RAM, RRAM. A lot of different new type of the device was proposed. Also, we like to try the architecture for integrations from the 2D integration to 3D integration. That means we achieve the same density, but we don't need the further scaling down the device. So today, for this technology, there are two ways for developing. So among a lot of different kind of new the proposed device, so RRAM and STT-RAM is the most promising one for the both industrial academics. So the second step I will introduce was resistance switch memory. It's very simple structures. So I think very easy to fabricate in a lot of laboratories. It's MSI structures. So usually, if the switch layer is insulated layers. If the switch layer form some of the conductive paths, that will behave like the low resistance states. Otherwise, if the conductive path was broken, then they will behave like the high resistance states. So this two states is very stable. Also, even remove the outside stress, it still can keep it. That means it can use for the non-volatile memory. So today they are demonstrating very good performance for this kind of memory. For example, the structure is very simple. Also, the good compatibility with the CMOS process. That's really important because the silicon technology is really established. If you like a new technology can use it is really important compatible with the CMOS technology because this is a baseline. If you like to block this baseline, is like so a huge challenge today. So also they are easily to screen down because we say the flash memory, their performance is very good, but they cannot further screen down. So if new technology, you need the further screen down. Also, there are larger on-off ratios. Because there are larger on-off ratios, that means even one device, maybe they have potential to store the several bits. That's very important for the high density. Also very fast, even can compete with the logical device. That's also very important. Because when you think a computer is so slow, that's not because of logical device, that's because of memory. You spend a lot of time to access your stored data. The computer time is very fast, but the access the stored data is very low. That's a big gap. So we need to find a new memory can fill these gaps. Also very good endurance, retention. That's typical for memories. The device, they are standard characteristics for the good device. So why when people think the RRAM is so important? For one reason is because the MIM structure is very simple. Also, they are easy to integrate with the backend logical technology. That means when your logical technology all the finished, you stop in the interconnect. Usually it's a couple. We can fabricate this RRAM in the couple layers, then connect it with a logical device. That's very convenient for the embedded application. I don't know do you know, for the CPU, 75% of the area is occupied by the memory, not by the calculation. So that means the embedded application to improve their memory performance is very important. Actually, also by standalone application. What means standalone? For example, this memory is a separate production. That means standalone application. If this for not only CPU, the DSP, like all the RFID, every production they have some embedded memory need to store data. That means for embedded application. So for standalone application, also RRAM very promising. We can say they can use this closed bus structure for the this architecture for integration. So this architecture can realize in the 2 dimensions very high density, the highest density, like the 4 feature square. This is a high density for the 2 dimensions integration. Even more, for this closed bus structure integrations, they are easy to stack layer by layer to realize the 3D integration. That's why RRAM was so promising by the industrial and the academic field. But actually for new technology, before they enter the real application, there are still a lot of challenges. For example, there are still a lot of materials can have this performance. For research is good. So a lot of people focus on this area, not the semiconductor guys, even the chemistry guys, physical guys, material guys, all research on the RRAM, because so many material can have this performance. But for real application, we should focus on the 1 and 2 materials. That's the important for real application. Also for the switch mechanism is still very clear, still needed to further the clarify. So for the production, so reliability issues are very important. For the screen down, even for the uniformity is very important, because for a single device, you don't need to care for the uniformity. But for the integration, the uniformity is so important. Also, compared to the flash memory used for 3D integration, so RRAM also has this potential. If not RRAM not this potential, is not accepted by industrials. So, but for integration, there are also a lot of challenges. So for my group, we involved in this area more than 10 years ago. So we do work of just focus on these 4 sides. One is the physical switch, try to answer the physical switch mechanism, also how to improve the performance, also the design, the circuit and reliability issues, also some 3D integration. But today we are mostly focused on 3D integration for this work. So today, because of limited time, I only introduce my work on how to understand the switch mechanism for RRAM. So we can see why understanding switch mechanism is really important. After almost 10 years in this field, they are still not very clear for this size. We can see after 10 years, the research, they generally accept for this memory RRAMs, when the conductive piece was formed, it is responsible for the low resistance states. But for this conductive piece was broken, it is responsible for the high resistance states. But actually, what's a dynamic process for this conductive paste formed and ruptured. Also, what's the filaments composition, also how many filaments can form. It's a lot of basic knowledge is still lacked. So that's why we focus on this research. So we just choose a very simple device platform for this research. So we choose zirconic oxide materials because we know this is a high K materials. It's compatible with CMOS technology. So the fabrication process also very simple. We just show here. Then at the beginning, we just, because our background is microelectronics, so the first step we still do some of the metrology. So at the beginning, we just say one device fabricated with the nature the low resistance states, the slopes, we can say they're close to 1. That means in the low resistance states, it's similar like the metal. They behave like a metal. So also we use the different the comparative current to the trigger of this device. Then we measure the reset currents relationship with the comparative current in set process. We can see this relationship. This is also the similar like the in the low resistance states. They behave like the metal. Also we can see there are different device area in the low resistance states. Is no relationship with device area. That's easy to understand if you agree in the low resistance states is conductive paste was formed because it is localized the responsible for the resistance. So for this evidence, this indirect evidence can confirm what's the mechanism for this kind of device, but actually we still cannot give what's the composition for these filaments. So then we do a temperature depends the measurements for so we can say for each different size device, we treat their thermal coefficients. They are almost the same. Also, if you compare this thermal efficiency with the carbon nanowires, they're almost the same. So deduced maybe this conductive filament was consistent with a copper. So then we try to answer it really can form the multiple filaments. So before we do some of the simulations, we can see usually the switch layer is the insulated material. There are a lot of defects. When it's stressed, so the highest electric field area, the more easy to form the filaments. Then if the stress increases the electric field, then another filament will form. That means basically they can form the multiple filaments. Then we try to conform it with the set up experiments here. We can see both in the set process and the reset process, they are not abrupt process. They have the step-like the process. So if you further slow down this process, we can see very clear see the step-like the behaviors. So to explain this phenomena, we propose the model for explaining multiple filament the switch mechanism. So the several filament was the parallel connected successively. Then based on this model, we can very well meet with the experiment results. Actually, this model, when published in API in 2009, is widely used for this society to explain this step layer, the multiple filaments phenomena. So then we try to understand what's the dynamic process for this filament forming. So this is very challenging jobs because for the in-situ observation for the vertical device is very challenging. So how to make a sample is very important. So we try a lot of different methods. Finally, we just choose the TM tip. When we're mailing these tips, we fabricate a total device on this TM tips. This is this detailed process. Finally, we can make a series of devices in one tips. So that means we can provide enough samples for the insert team observation. So then we can see when the stress, also we can see when you stress slowly, then the set process take place. Meanwhile, we take the image here, we can clearly see the filament was forming here. Also for the opposite sides, when we use the reset process, the current decreased. That means the filament. Also, the formed filament is disappeared. That's the first time we get the image for this dynamic process. So this is a picture cut from video. More clearly, this is a fresh device. When stressed, we can see the filament formed. Also, we can see the second filament formed. Meanwhile, we can see the curve. This set process take place here. So also for the rupture process, this is the device finally the set already set. We can clearly see the filament formed here. This is filament. When you use the rupture, the first reset process, we can after first reset process, the filament already broken. But we don't set it again. That means we further the broken. Then after 1 to 1, finally the total filament can broken. So let's give the hardware evidence what's a filament, the glowing and broken process. So to understand the mechanism is not only for the interest in physics, it's also really important. But for the application, it's really to how to guard the applications. Well, now, for the RRAM, the big issues is this uniformity issues. We can say there are larger distributions. That's very bad for integration because one device is the high resistance stays here, analysis here. That's not good at it. So why cause this the larger distributions? We try to understand. That we can clearly see that's because the filament forming and rupture process is a random process. That's a big problem. So why there are larger distributions. So based on this knowledge, we try to, if we can control the filament forming and rupture process, that means we can get a very tight distribution for this the device. So based on this idea, we say here, if in this device we give the nanocrystal here, anything also is the tip is also okay. When the stress, the highest electric field is in the top of here, then maybe we can induce the filament forming along these areas. That's our ideas. So based on this idea, we do some simulation. We can clearly see is the highest electric field is just on the tip of this nanocrystal. Also, except this tip, the electric field decreases dramatically. Also, we simulate a different nanocrystal design relationship with the electric field. Based on this simulation results, we like to design an equipment device. This device is very simple. This idea is important, but the fabricated device is simple. We only in the bottom electrode with deposition very thin, 3 nanometers the couple. Then after annealing, this 3 nanometers couple layer become the separate nanocrystal. This team clearly see this couple nanocrystals. So then the fabricated device. We measure this device, we can see the performance improved dramatically compared to now this nanocrystal layers. Also, we can see the uniformity is very good, both the high or low resistance states, reset and reset. Then they also can demonstrate very good multiple level storage performance. That's good for the high density applications. So let's not give the direct evidence the filament was controlled by the nanocrystal. But then we get the TEM, we can clearly see this filament, they are growing along this nanocrystal. Let's give the hard evidence we can control the filament just growing around this the nanocrystals. Also, furthermore, we analyzed what's the composition of this filament. We see this is the EDS analysis. We can see this filaments. Then from we can see clear see this filament is a silver. So why this change the silver? Because the one electrode become the silver. Because usually for TEM the host is a copper coin. So if you use, they still use the copper is a baseline, signal is very strong. Also, if the further mapping, we can clearly see this is this is a copper, it's very uniform. For zirconium, also very uniform. Only in silver, you can see this electrode, this filament. That's totally give the evidence. This filament can controlled by the strong the electric field. Also, the filament the composition is very clear show here. So let's I like to finish my today's talk. So for my work today's talk I will focus on the RRAM's switch mechanisms. We do some work firstly based on the electron measurement. We indirect conform to the filament. In the RRAM, the switch process is the filament form and rush process. Then we get the direct evidence to review to demonstrate the dynamic process for the filament forming and rupture process. That's very important work. So this work published in the advanced material, also the high cited paper today. Also, we proposed a model to explain the multiple filament forming and these mechanisms. So finally, after we understand this is the mechanism, we try to use this understanding to get the more better device performance. So we propose to use the added some nanocrystal to control filament forming and rupture in the fixed positions. Let's make the device get the better performance. So I'd like to thank my colleagues and my students. So in my groups, my group capacity is large, but do the RRAM research is only these three guys. This actually the one is my former students. Then this is some of the PhD students and some also already the graduate. So one is now, so this is not updated. Not actually he now is not in the year is a staff is a faculty in the American universities, noise universities. Also some enter industries. So also thanks some funding support from the mainland China. Also, thank you very much.
Thanks very much, Ming. I'm sure there are some questions.
So I'm not the expert on what we're talking about. You mentioned lots of filament. I want you to give more explanation and discussion. What's the filament? How is it formed? Isn't you're talking about the memory material from the filament?
Yeah, actually, this is a good question, but actually, so we can see these cartoons. So usually the RRAM, the switch layer. So both this is electrode is metal. The switch layer is an insulated layer. Usually they are not conductive. But
Is it that you always mention high K material, the
Not only high K, a lot of even polymer, even some like the PCMOC, a lot of material have this performance. But
So you're using the inorganic zirconium oxide as a model?
yeah, actually, because this material may be more easy to realize commercial application. Yeah. So then, when you actually for this the materials there has a lot of defect. When you get some of the stress in this, some of the conductive pairs were formed. That depends on different material, different device, even the electrode. Some filament is real metal, but some filament is only the oxygen vacancy.
So that means that material will change some phase when you apply voltage?
Not change phase. This is just change some of the conductive behavior.
Yeah, so
Yeah.
what's the filament form? Anyone knows?
So that's very complicated. I'm not. So usually, if for
So the consequences from the filament that is conductive improved?
improved. Yeah.
So then you can see it. Actually, you can see from
Yeah,
here.
that's our work. They also the first time in the world see this filament.
So anyone in the field have explanation? What's the reason for the formation of this filament, or in the material side of research?
Because you see, all is a special kind of the device. You can see one electrode is the copper. You know, copper is very easy to the oxide. So you can become after stress the electric field. They can become the ion, not the element. Then the ion moved along the electric field, go to another electrode, capture the electron, then become oxide to the element again, then form the filament. That's the real mechanism.
If you compare the RRAM with the flash memory that you compare, it is much faster, low power consumption, and scalability compared to the flash memory based on NAND gate. So my first question is, what's the most challenging issue that is not commercialized yet after 2011, right, when it was 14 after 3 years, and they said, okay, it takes at least 2-3 years to be commercialized. And my second question is that, as I know, the Crossbar company working on this kind of memory for 3 years, and 2 years, I guess. And what you are doing in research in university is just following what you are doing in companies, or not two different areas that you are working on something else and you are working on commercialization. I don't know how this area are connected together. Or your researcher, you could help them to make it faster.
That's a very big question. So I try to answer your questions. For your first question is this kind of memory was their challenge. So it is still cannot compete with a flash memory, honestly speaking. But it's already commercialized for the embedded application. There are two companies commercialized. One is the Japanese company. I'm sorry, I forgot the name. They are used for their display. So but both is used for the embedded application. The bigger advantage for RRAM is their operation voltage is the same as the logic device. You know, flash memory program erasure use high voltage. That's bigger problems. So for us, we are the research institute. So actually, I think my personal understanding, we like to do some advanced researches. We need to go, I think, beyond the industry. Because the industry maybe just focus on the already mature the technologies, we are go more ahead. That's the difference. So actually, we are also some collaborate with local industry. For all groups, we are separated. Most of our staff is do some of the more commercialized work with the local industry. But for students, they are doing more advanced technology for the research. Also, my personal interest in also on the research.
Thank you.
Diane?
Yeah, have you done this reliability test? How many times?
Sure, definitely.
Yeah.
10 to 9. Reliability is very good. So we also even do 1 kbit circuit.
There was another question.
Let's do the Nano-Fabrication test
Mm.
where you started from. If you want to make some nano metal wire, parallel wire, how small we can make it now with current technology? What's the periodic structure? How small it can become?
Because we use EB lithography,
Yeah, how
for
small?
the can down to 10 nanometer.
10 nanometer.
对, but it's very challenging.
So 10 nanometer is a periodic structure, means nano wire is about 4 or some nanometer.
But usually nanowire is very difficult for fabricate on nanowire. Usually we fabricate on the silicon wafer. But this 10 nanometer is a resistance pattern, not a real metal pattern. If you transfer to metal, now the record is 13 nanometer.
30 meter is periodic structure,
Yeah.
so the wire will be even thinner.
What do you mean why? So this is just not the line space, just the line is 13. Line space is 26. That's me.
Any other questions? If not, please join me in thanking Dr. Liu for a very interesting talk.
Thank you for all your attention.